Often in motion with constant acceleration problems, you care about distance and velocities, but not time. We've seen a few examples already, such as when we want to know how fast a gannet is moving when it hits the water, known its initial height. We can analyze such situations as two-step problems. First, calculate time, and then second, substitute that into the other equations. Alternatively, we can use algebra to algebraically solve for time, substitute that into the other equation, and then we have a new equation which we can solve in a one-step method rather than two. And for simple problems, these two approaches more or less take the same amount of time, doing it as a one-step problem or a two-step problem. So you don't really have to worry about which one you do. There are a class of problems, however, where the first step, the calculating time, requires solving a quadratic equation. Under those circumstances, it's nicer to have the expression where you've already done the elimination. So here we're going to show you how to do that elimination and the new one-step approach. All right, so the classic problem to think about here is what I like to call the Bambi problem. So you are driving along a road at, say, 13 meters per second. So 13 meters per second is about 30 miles an hour. Okay, so you are cruising along, and then suddenly you see a deer. You slam on the brakes. Okay. The deer, 15 meters away. Do you stop in time? Okay, so the acceleration of a car during braking depends on a lot of things. It depends on your tires, details of the auto-lock braking system controls. We'll learn more about this stuff when we talk about models of friction. But a car with decent tires can brake with an acceleration of around 7 meters per second squared. And a reasonable way to model what's happening here is think about it as motion with constant acceleration. And as I said, the acceleration should be around 7 meters per second squared. And I guess in this case, if I make this the plus direction, then I guess the acceleration is. Okay. So if we were to solve this using the two-step method, we'd start with saying Vf minus Vi equals At, motion with constant acceleration. And we know what the final velocity is. That's 0. We know what the initial velocity is. That was 13 meters per second. We know what the acceleration is. 7 meters per second squared. And then we could calculate time. And then the next step to figure out how far you go during that braking event is I would use that the distance traveled is the initial velocity times time plus 1/2 AT squared. And I could take this time that I calculated here and plug it into these two places and calculate the distance. Okay. So we're going to do that exact same process, but do it algebraically. And in this particular case, we're not actually going to get much efficiency from that because this first step of calculating time was relatively easy. Okay. Where it becomes really useful is if you're given the distance, in which case solving this equation for time is a quadratic equation, and then substituting that into here is a pain. Okay, but the formula we're going to get is going to be good no matter which direction we're trying to go. And that's why this is useful. All right, so we start by solving this equation algebraically for time, which gives time Vf minus Vi for A. And then we substitute that into this equation. So we get delta x equals Vi. Okay, actually, one more step before doing this. This is going to be a little bit of a pain. I can make it a little bit easier if I do some factoring. So I'm first going to factor a factor of time here and write this as time Vi plus 1/2 AT. Right, that's going to make my life easier. So let me do it now. So I first have this time, which gives me a Vf minus Vi for A. Right, so that does this piece. Okay, and then I have this piece. And that piece is Vi plus 1/2 A Vf minus Vi for A. Okay. Now I'm just going to simplify. I can cancel these A's, and then I multiply, I can add this up, so I get 1/2 of a Vf, and then I get a Vi minus 1/2 of Vi, that's a plus 1/2 Vi. Okay, putting this together, I'm going to factor 1 over A out of this. So I get 1 over A, Vf minus Vi. I'm going to factor 1/2 out of this, and I'll put that factor of half at the end. Vf plus Vi is 1/2. And now I just multiply this out. And if you've multiplied out things like this before, you know that it actually has a simple expression. So I'll bring this 1/2 and the A together to get 1 over 2A. Vf squared minus. What a surprisingly simple result. So the distance gone is related to the initial and final velocities and the acceleration in this manner. So in the present case, let's put in our numbers. So the acceleration, we had said, was supposed to be minus 7 meters per second squared. And then Vf, we said, was 0. And Vi was 13 meters per second. Okay. And if I go and multiply all that out, I get that this is 12 meters. Looks like we don't get any venison tonight. Excellent! This is smaller than 15 meters, so we stop before we hit the deer. I'm so glad that deer is safe.